Hello, my name is Magnús Tumi Guðmundsson and I'm a professor of geophysics at the University of Iceland. I do my research within the Nordic Volcanological Center at the Institute of Earth Sciences. My research over the years has been very much on volcanoes and geothermal areas under glaciers. We have a lot of those here in Iceland. But not only in Iceland, there are also similar volcanoes in Alaska, in Antarctica, and on several stratovolcanoes in South and North America. Volcano-ice interaction is very common. This video is on how we use aircraft to study both volcanic and geothermal activity under glaciers. This is very important in Iceland, where flooding caused by geothermal and volcanic activity is a very common form of volcanic hazard. In Iceland, some of the most active volcanoes are covered by ice. Over 50% of all eruptions in Iceland start under glaciers, and the ice may be many hundred meters thick in some places. Eruptions are most common in the large central volcanoes of Katla and Grímsvötn. All their eruptions involve volcano-ice interaction. This also applies to Bárðarbunga, Eyjafjallajökull and Öræfajökull, and they have all been active in the recent past. We also have geothermal activity under the ice. The depressions form in the ice surface where the geothermal heat melts the ice from below. These depressions are called ice cauldrons. So, how do we monitor volcanic and geothermal activity under ice? The monitoring of seismic activity is always very important. Together with GPS and INSAR, seismic monitoring is our main tool in detecting magma movements in the crust. When a volcano is covered by a glacier, GPS and INSAR may also help, but if the ice covers most of the volcano and the surrounding area, the glacier masks the small signals that, for example, are caused by the inflation of a crustal magma chamber. We may be left with looking at GPS signals from possibly just one station to study possible magma inflation. But we can also look at thermal signals, increased melting of the ice, for example. This signal is seen before some volcanic eruptions under glaciers. In the case of an eruption under glacier, the ice melting can be extremely fast. Such an eruption under thick ice creates an ice cauldron over the eruption site. The ice is melted and the water often flows along the glacier bed away from the eruption site. When the meltwater reaches the margin of the glacier, we get large volumes of water forming a major flood called a jökulhlaup. Also, when we have an eruption under the glacier, we need to know what is going on. How large are the changes? How much ice is being melted? What is the hazard? We probably get the best maps available by using satellite data. This includes both the surface of a new lava in an effusive eruption or the surface of a glacier. Often, the satellite is only available once every 24 hours. And it also requires visibility, that the area of interest is not covered by cloud. The availability of satellites is getting progressively better, but conditions and the present availability may mean that no data can be obtained for days. Therefore, during crisis, it is very important to have access to aircraft. We have used two different types of aircraft surveys for monitoring of volcanic activity in Iceland. One method is the rapid measurement of the height of the ice surface using ground clearance radar. Another method, used for the first time in the Eyjafjallajökull eruption in 2010, is the imaging of the surface using SAR radar on board the aircraft. In this video, we show examples of both methods. The method used over the last 25 years in Iceland is the profiling with the Icelandic Aviation Service aircraft. It has a system of real-time differential GPS and ground clearance radar, and the absolute elevation accuracy of the system is about 2 meters. Soundings are taken 4 times every second, giving us a measurement of the distance to the ground every 20 meters along the surface. The radar has a frequency of 4.3 GHz and a wavelength of 7 centimeters. We get the best results by flying about 100 meters above the surface. Here you see schematically how surveying is used to map the changes that happen when a subglacial lake, formed by a geothermal area beneath an ice cauldron, is drained in a jökulhlaup. The example is the eastern Skaftá cauldron in northwest Vatnajökull. It typically collects water for 2 to 3 years and is then drained over a few days. These changes have also been studied very effectively using satellite mapping before and after the event. Profiling with a survey aircraft has been used in many events, both volcanic eruptions under ice and what we can call unrest under the glaciers. These events are the Gjálp eruption in 1996, the Grímsvötn eruptions in 1998, 2004 and 2011, the monitoring of Katla since 1999, where periods of high activity in seismicity and geothermal activity have alternated with periods of low activity. The caldera subsidence of Bárðarbunga and the small subglacial eruptions that took place during the rifting event in 2014-15. The increase in geothermal activity in Eyjafjallajökull in 2017-18 caused by a magmatic intrusion at a few kilometers depth. And occasionally we have used the profiling to map changes in the lava forming in the eruption at Fagradalsfjall in 2021. The results of the surveying are profiles of the glacier surface. Processing of the data is usually very simple, and the first profiles can be ready for display and study less than an hour after the aircraft has landed. During volcanic eruptions, we see the depths of depressions in real time on a display on board the aircraft. This allows quick estimate of the magnitudes and how fast things are happening while still in the air. This speed of delivery matters during eruptions. It is important to estimate the situation as fast as possible. The second method of monitoring volcanic activity in a glacier from aircraft is very different. The SAR radar uses a similar frequency as the air clearance radar, that is several gigahertz, and the wavelengths are a few centimeters. The radar signal is transmitted sideways and downwards. The aircraft is flying at 4 to 5 kilometers height and perhaps 20 to 30 kilometers away from the place of interest, in our case a volcanic eruption site. The radar signals that come back to the aircraft have very different character depending on the surface that is reflecting them. A vertical wall at right angles to the radar beam will send a very strong signal back to the aircraft, while a low-sloping surface will send back a much weaker signal. The SAR radar detects all this and presents a signal intensity image. This image can be, for example, similar to a shaded relief map of the eruption site. And this system sees through cloud, so the aircraft can be flying at a safe distance, upwind of the eruption, far away from the volcanic eruption plume and ash in the atmosphere. This was the great advantage of the system during the Eyjafjallajökull eruption in 2010, when the craters were covered by cloud in the first 3 days. During those 3 days, we obtained many images showing how the ice cauldrons grew as the eruption progressed. So, to summarize, a well-equipped aircraft is an important tool in places like Iceland when it comes to monitoring of eruptions and geothermal unrest under the glaciers. Profiling surveys are simple and provide accurate data, and they do it very quickly. Use of synthetic aperture radar is very good to monitor volcanic craters and glaciers during eruptions, as the data can be gathered at a safe distance from the eruption. The mapping of ice surfaces for long-term monitoring is now increasingly done using satellites, such as the French Pléiades. But we still need aircraft because the aircraft is available any time of day, provided the weather allows flying. Some examples of how the methods are used and the results obtained can be found in the publications listed here.